Today's lesson about cryptography has to do with something called modular arithmetic. Shoot. Okay, so today's class is going to be about a new kind of code. We're going to do two new kinds of code, and they're based on something called modular arithmetic, which I already primed you about when we did Pascal's triangle and we talked about remainders, dividing, and what kind of remainders you can get. That's what modular arithmetic is all about, remainders. So for example, suppose today is Monday, and you want to know what day of the week it will be 72 days from now. Well, you know that every 7 days you return to Monday. So we can divide 72 by 7, and that will tell you how many weeks have gone by, but the remainder tells you how many days after Monday it'll be. Okay, so if we do 72 divided by 7, 72 days from now, divide by 7 days in a week. So you go, well, 7 goes into 7 once. Subtract, bring down the 2. 7 goes into 2 no times, right? So this is my remainder. It's 10, remainder 2. So 10 weeks and 2 days later. So it'll be Wednesday. So 72 days from Monday is the exact same day as it would be 2 days from Monday. It's 10 weeks later. Okay, so we use the remainder to answer questions like this. So another way to do it, another time we do this is with months. If we say it's currently April, what month was it 27 months ago? It's under my keys. So if it's currently April, we want to figure out what month it was 27 months ago. So there are 12 months in a year, so every 12 months we return to April. So we divide 27 by 12. When we do 27 divided by 12, 12 goes into 27 twice, right? And 2 times 12 is 24. My remainder is 3. So 27 months is 2 years and 3 months. So if I want to know what month it was 27 months ago, I have to go back 3 months, right? 2 years and 3 months ago. So I go back 2 years, lands me back at April, and then I go back another 3 months. And we get to January. March, February, January. That make sense? Okay. So we're going to base a whole new kind of arithmetic on the arithmetic of remainders. Okay, all we're going to care about is remainders now. So keep in mind the number that you're dividing by to get the remainders. That is called the modulus. Okay, the number that you divide by is called the modulus. The days of the week example, the modulus was 7 because I was dividing by 7. And in the months example, the modulus was what? 12. Good. So remember, when you divide by 7, the only possible remainders are 0, 1, 2, 3, 4, 5, and 6. Why can't 7 be a remainder? That's how many days in a week there are. So if you have a remainder of 7, you have a whole nother week. So that's really a remainder of 0. So each of these remainders, 0, 1, 2, 3, 4, 5, and 6, represents a different day of the week. So we could make a little table where we let Sunday be day 0, Monday be day 1, etc. Okay. So if I ask this question, today is Thursday, what day will it be 5 days from now? We could represent that question as 4 plus 5, right? Because today's Thursday, which is day 4, plus 5 more days, right, would be, in standard arithmetic, that would be 9, right? But there is no day 9. So what I do is I take my 9 and I divide it by 7 and give the remainder. Okay, so I take the 9, you divide by 7. 7 goes into 9 once with a remainder of 2. So the answer is 2, Tuesday. And you could also think of it like this. You start on day 4, Thursday. We're going to start here. And you go 5 days from now. 1, 2, loop around, 3, 4, 5. And you land on Tuesday. So you can do it by looping or by adding the two numbers, dividing by 7 to get the remainder. If we were adding, 150 instead of just 5, it would be much easier to do the addition and divide by 7. Here it was easy to count, but you can do it either way. So if today's Thursday, and we want to know what day it is 1,000 days from today, we say, well, today's Thursday, that's the number 4. Add 1,000 days to that, and we get day 1,004. And I have to know what day of the week 1,004 is. So you divide it by 7 and get the remainder. So I take 1,004, divide it by 7. We say, okay, well, 7 goes into 10 once. 1 times 7 is 7. Subtract. Everybody remember how to do this? Okay. 10 minus 7 is 3. Bring down the 0. 7 goes into 30 4 times. 4 times 7 is 28, and subtract. And 7 goes into 24 3 times. 7 times 3 is 21. And 3 is my remainder. Okay. Yes? So the answer doesn't matter at all. The answer does not matter at all. Just the remainder. What does 143 represent, though? How many weeks have passed? It's been 143 weeks and 3 days. So to figure out what day of the week it is, we can say, well, the 143 weeks don't matter, because every time a week goes by, I land back on Thursday. So I would say I made 143 loops around my little chart here, and then I just have to go 3 more days. 1, 2, 3, and it's, oh, sorry, so 3, it's Wednesday. Wednesday. Remainder 3 gives me Wednesday. If we're working with months of the year instead of days of the week, the modulus is 12. So we can also number the months with our possible remainders, which are 0 through 11 when you divide by 12, because a remainder of 12 is really a remainder of 0. So we could make 0 January and 1 February like we did for the days, where we made Sunday 0 and Monday 1. But this would get weird for us because we're so used to having January be 1. So let's call January 1 and February 2 up to 11 for November. But we can't use 12 for December because 12 isn't one of our possible remainders. You can only have 0 through 11. So we'll use 0 for December. So now we want to think about this question. If it's currently March, what month was it 8 months ago? So to represent this with an equation, I would have 3 for March, and 8 months ago minus 8. So in normal arithmetic, my answer would be -5, right? But -5 isn't one of my possible remainders. I have to come up with a number between 0 and 11, because those are my months. So I have to figure out what month -5 is. You could try to do the division thing like we were doing before, try to divide -5 by 12 and get the remainder, but it's tricky with the negative sign, how you actually do that. So instead, we're going to remember that you can always add or subtract 12 from any number, and that won't change the remainder you get when you divide by 12, right? So if I add 12 to -5, I get 7. So -5 must have to be July. If -5 is a month and you add 12 months to it, you should land on the same month, which is 7. So that's July. So our equation looks like this: 3 minus 8 equals 7, right? Which is, it looks weird because this is a new kind of arithmetic. And in fact, pretty often when you see modular arithmetic being done in a textbook, they will use a special equal sign that has 3 lines instead of the typical one to just remind you they're equal, but only in the sense of remainders. So we can do modular arithmetic with any modulus bigger than 1. You can use any number as the number you divide by. And we're going to apply these ideas to cryptography, which means we're going to use a modulus of 26. Why do you think 26? 26 letters in the alphabet. So each letter of the alphabet is going to be represented by a number from 0 to 25. So 0 is going to be A, and 1 is going to be B, 2 is going to be C, etc. It's going to be really handy for you to have the alphabet written out with the numbers that they're associated with, and have it with you like whenever you're working on this, because it gets to be a pain to have to count all the time. So why don't you go ahead and do that? Write yourself out a little key where you have the alphabet and you put the numbers. Make sure you start with 0 and not 1.